Rolling motion, it is a combination of pure translation and rotation. In this motion at any instant of time, the bottom of the rolling body, which is in contact with the surface, is at rest on the surface. The center of mass of the body is in translatory motion. The situation is shown for a disk. The disk has radius r and its angular velocity is omega, and this is the point of contact which is represented by P0. This is the top point P1, and any point in the disk is P2, and the velocity of center of mass is VCM. The rotation and the instantaneous axis of rotation passes perpendicular to this point, instantaneous rotation axis. The rotational motion of the disk is about its symmetric axis, which passes through C. Consider the particle at point P2, that is point P2. The velocity of the particle at point P2 is the vector sum of velocity VCM and VR. Here, this point have two velocity. One is equal to VCM and another is equal to VR, because it is rotating like this about C, and so the velocity of point P2 will be V2. That is V2 vector equals to VR vector plus VCM vector, where VCM is the velocity of center of mass and VR is the linear velocity of the particle due to rotation about CM. The magnitude of VR is VR equals to mode of VR vector equal to omega into R2, where R2 is the distance of particle from the center of mass. Now at point P0, that is at the contact surface, VR vector is opposite to the VCM, and so V0 will be equal to VR plus VCM equals to omega R into minus I cap, because VR is in this direction and VCM is in this direction. So VCM will be unit vector I cap, and omega VR has unit vector minus I cap. Now V0 vector will be VCM minus omega R into I cap. Now since in pure translatory motion, the point of contact is instantaneously at rest. The point P0 is so point P0 is instantaneously at rest. This implies V0 equals to 0 and VCM minus omega R into I cap equals to 0. This gives VCM equals to omega R. That is the velocity of center of mass of the rolling body is omega R. Now at point P1, that is at the top of the point, VR vector and VCM are in the same direction. Hence V1 vector equal to VR plus VCM omega R I cap plus omega R I cap equals to omega R I cap, or magnitude of V1 vector is V1 equal to 2 omega R. That is top of particle at top have velocity 2 omega R. So there will be for pure rolling body, this is the condition. If a body is moving with the angular velocity omega and center of velocity of center of mass is will be given as omega into r if the rolling body have a radius r, and the velocity at the point at bottom will be 0, that is contact point will be 0, and velocity of at top point will be v equals to 2 omega r given by this value, that is point at top the velocity will be given as 2 omega r. This is the condition for pure rolling. Now kinetic energy of a rolling body. Because in a pure rolling body there are two types of motion, translation and rotation. So there will be two kinetic energy. So here we have written K equals to K translational plus K rotational, that is translational kinetic energy plus rotational kinetic energy. Now translational kinetic energy will be 1 by 2 m VCM square and plus rotational kinetic energy 1 by 2 ICM omega square. Where VCM is the velocity of center of mass, ICM is the moment of inertia of the body about the axis passing through the center of mass and perpendicular to the plane of rotation. Now we know that VCM equals to omega r. This gives omega equal to VCM by r. And also we have formula ICM equals to m into k square, where k is the radius of gyration from the previous theory. Hence k equals to 1 by 2 m VCM square plus 1 by 2 m k square VCM square by r square. Putting the value of ICM and omega in terms of mk square and VCM by r, we get this value. And so taking 1 by 2 m VCM square from both term, we get 1 by 2 m into VCM square into under bracket 1 plus k square by r square. Now this formula can be used to get the total kinetic energy of a pure rolling body. Now based on this formula, we are going to solve a problem. Here is the problem given. Three bodies, a ring, a solid, a cylinder, and a solid sphere roll down the same inclined plane without slipping. They start from rest. The radius of the bodies are identical, and which of the bodies reaches the ground with maximum velocity. Now the condition is shown here. This is a inclined plane and body is set free from A to roll down, and body comes at B. So we have to calculate the maximum velocity of three bodies, which body have maximum velocity at point B. Now we know that the ICM ring, that is moment of inertia of ring about center of mass is mr square. Similarly, ICM cylinder is 1 by 2 mr square and ICM sphere is 2 by 5 mr square. This value has calculated earlier. Now, if there is no loss of energy due to friction, then from conservation of mechanical energy, here we are considering that body is surface is frictionless. So mechanical energy at A that is at A will be equal to the total mechanical energy at B. So now we know that mechanical energy is equal to potential energy and kinetic energy. So potential energy plus kinetic energy at A equals to potential energy plus kinetic energy at B. This implies here, because body is at at rest, so velocity is 0. So only potential energy will be at this point. So we have written mgh plus 0 because kinetic energy is 0, velocity is 0. And at point P, and potential energy at point B will be 0 because height is 0. So 0 plus, and kinetic energy is given by previous formula 1 by 2 m v cm square 1 plus k square by r square. From this formula we get VCM square equals to 2gh by 1 plus vs 1 plus k square by r square. From this formula we see that the velocity of center of mass does not depend on the mass of the body. Now from ring, for ring, k equals to under root ICM ring by m equal to under root mr square by m. This implies k square equals to r square. Hence VCM ring under root 2gh by 1 plus k square. Putting the value k square equals to r square, we get under root 2gh by 1 plus r square by r square under root 2gh by 1 plus 1 under root 2gh by 2 equals to under root gh. This is the center of mass velocity of center of mass of ring given by this value. Now for cylinder K equals to under root ICM cylinder by M, and under root 1 by 2 mr square divided by M under root r square by 2. Hence this implies K square equals to r square by 2. Hence VCM cylinder under root 2 GH by 1 plus R square by 2 into 1 by R square under root 2 GH by 1 plus 1 by 2 under root 2 GH by 2 plus 1 by 2 under root 4 GH by 3 or under root 4 by 3 into GH equals to 2 by root 3 root GH. So this is the velocity of center of mass for cylinder at point B. Now for solid sphere, K square equals to IACM into solid square divided by M. K square is 2 by 5 M R square by M, 2 R square by 5. Hence VCM solid sphere equals to under root 2 GH by 1 plus K square by R square equals to under root 2 GH by 1 plus 2 R square by 5 into 1 by R square under root 2 GH by 1 plus 2 by 5 under root 2 GH by 5 plus 2 by 5 equals to under 10 GH by 7 or equals to under 10 by 7 into under root GH. Now from these three value we see that this value is maximum. This is the maximum value for the velocity of center of mass. So a spherical body will have the maximum velocity at point B.